Welcome to the Spoon Podcast, where we talk to the builders and makers on the front lines of the food tech revolution. I'm your host, Michael Wolf. Startups in the cultivated meat space have had a hard time of it the last couple of years as they try to figure out how to do something that's never been done before. Grow meat and lots of it, not by raising and feeding cows or pigs or chickens, but by growing meat cells in big metal vats known as bioreactors. 10 years after Mark Post created his first lab-grown hamburger, companies who've collectively raised billions of dollars to figure this problem out are moving really slowly. Some have gone out of business and others will soon follow. Part of their challenge is trying to figure out how to get the meat cells to grow. Much of the technology to do this has been borrowed from the world of pharma, an industry where you can charge $1,000 or $10,000 for an ounce of a cancer drug. These cost dynamics obviously will not work when you're making a chicken sandwich. Deniz Kent thinks he may just have the answer. His company, Prolific Machines, is replacing the expensive growth medium that the industry's been using and struggling to get to work with maybe the cheapest source of energy in the world. In this podcast, you'll hear the story of his company and how they are trying to save the cultivated meat space with light. So let's get to my conversation with Deniz Kent.
I'm Deniz Kent, co-founder and CEO of Prolific Machines.
Deniz started his career as a scientist doing work in the world of T cells, which are part of the immune system and developed from stem cells in bone marrow. They help protect the body from infection and may help fight cancer. He eventually went to work for a large pharma company and worked on a single-dose cure for asthma. And he also worked on a bispecific antibody that would help reprogram the human's immune response to respond to allergens with tolerance instead of inflammation. And it was during this work that he started to become fixated with a certain type of amphibian.
And while I was at GSK, I became very interested in salamanders and axolotl, and especially in their capabilities. You could cut off their arms and legs and they would regrow their arms and legs. And I was just like, I want to understand how this works. This is fascinating. And I was especially interested in whether we could do this in humans. And so I was fortunate and lucky and got accepted into one of the best liver stem cell labs in the world. And I started studying the liver because the liver is basically the closest that humans get to being like salamanders. We can cut off 2/3 of our liver and it will regrow.
While he was at the Liver Stem Cell Lab, Deniz did a lot of important work, such as the world's first single-cell RNA sequencing on the human fetal liver, single-cell RNA sequencing on the human adult liver, and did a lot of drug screening for various genetic diseases that impact the liver. During this work, Deniz started to think about the current tools that scientists had for research.
I spent a lot of time on the bench doing experiments, and one of the things that I learned was the tools that we have to control cells are not that great. And the tools that we have really are molecules. The molecules can come in two different categories. One is chemicals, and the other is recombinant proteins. These are the two big levers that we have to pull, and we mix up different combinations of chemicals and recombinant proteins, and we add them to the cells, and we hope for the best.
This cocktail of chemicals and recombinant proteins was how he and others grew the cells for their research. But Deniz found there were problems with these tools, one in particular.
And these molecules, all of these are molecules. And so these molecules are, in many cases, more expensive than gold, gram for gram. And so it limits what you can do with biology. So if you try and use these expensive inputs to make commodity products, the economics don't make sense.
One of the commodity areas that Deniz is referring to is cultivated meat. The world of cancer and pharma research that he had lived and breathed in for years could afford to have inputs that were more expensive than gold. But when it comes to growing something that may ultimately be sold at a McDonald's drive-thru, the math just didn't work. This led him to explore other tools that were more affordable and more scalable.
I believe that cultured meat can work, but in order to make it work, you have to use light to grow and control the cells, because light is the only input that will be cheap enough where the economics make sense. And light is the cheapest input into biology because LEDs have been commoditized by the consumer electronics industry, and electricity has been commoditized by civilization. And so light represents the sort of floor for how cheap biology can ever be. And so that's the obvious reason to use light, but there are several non-obvious reasons to use light, the most important of which is control. And there's two axes to control. One is the time axis, i.e. the timing of the signals. And if you can control the time axis, you can get large yield advantages. and the other is the space axis. If you can control the space axis, you can create patterned products. Light is also the most reproducible input into biology. It's inherently sterile, and it's easy for machines to understand and implement. So the big picture vision with Prolific is building the world's first machines that can truly control biology, that can interact with subcellular biology specifically.
Before we dive into that and talk more about it, so I want to hear a little bit about how you just stumbled upon this idea. Was this something you were doing? You said you spent a lot of time on the bench. At some point, did this aha moment happen? Did the light bulb go off in your head and you said, hey, this is something that can be applied and I can start a company around this?
So controlling cells with light exists independently to Prolific. There's a field called optogenetics, but almost the entirety of the optogenetics field was focused on the brain and understanding the brain. And optogenetics was being used as a tool to activate neurons using light. And people have created basically systems where you can study how mice work. So you can build like remote control mice using this. So you can shine light on a certain part of their brain and you can make a mouse turn left instead of right, or you can make a mouse eat or not eat, or have sex or not sex, you can, by shining just different wavelengths of light in different places of the brain. At this point, people usually ask me, can you do this for my children?
Yes. Yeah.
It is scientifically conceivable to make remote control children, although morally questionable and outside of the scope of what Prolific Machines does.
I'm just fascinated by this, by the way. You're not obviously shining a flashlight into the brain, but how is this signaling into a brain of a mouse?
So for clarity, this is not what Prolific Machines does, but I will just explain how this works. To do optogenetics in the brain, you have to drill through the skull, and it's usually done with a laser that is then slid through the skull to shine and different parts of the brain. So what Prolific does is uses light outside of animals in bioreactors or in various 2D contexts in order to control cells. And this application in a manufacturing context had never been done before. And I was exposed to optogenetics from an R&D in an R&D context through my PhD. And I was also exposed to cultured meat because I love eating meat and I feel terrible about it. And I really wanted to have cultured meat work because I want to have a meat-heavy, guilt-free life. And it seemed like cultured meat was the best way for me to be able to do that. And so I was very passionate about cultured meat. I got really excited about it. And then the more I learned about it, basically went through the whole hype cycle.
When you realized how the existing way of doing it with recombinant proteins, you then spun into the trough of disillusionment and became a cynic. When did you connect the idea of, okay, I'm cynical about this, not going to work, and then, oh my gosh, there's this idea of light?
Yeah, that happened during my PhD, where I was getting exposed to optogenetics as a research tool, and also was learning about cultured meat and reading all the papers and the TEAs and talking to people in the industry. And it crystallized in my head that cultured meat, if you have to use inputs that are more expensive than gold and you're trying to make a commodity product, this does not make sense. You don't even need to be a genius to realize that. And I was like, well, how do you get rid of these inputs? How can you do that? And what is the cheapest thing that you could use? And it kind of dawned on me that light is the best thing to use because there's nothing that is cheaper than light. And so light will be the floor for how cheap this can be. And if you use light, it's not just about bringing down the cost, you can also increase the quality because we can use light to control every aspect of the cell. So you can make it more nutritious, you can make it more delicious, you can bring down the cost, you can co-produce other proteins. So there's a whole bunch of interesting things that you can do with light that you also can't do very well with molecules. And so it's not just about bringing down the cost. I do think that in the future, cultured meat will be the primary way of producing meat. That may take decades or maybe even 100 years to materialize, but I believe that is the future that we're heading towards. And I think the primary driver of that will be companies wanting to make more money. And so we are actually we're basically proving out this hypothesis that growing meat with light is the most profitable way to make meat. And we believe that it is. We believe that if you use meat to grow light, you can make a meat business with 40 to 60% gross margins. And if that is true, capitalism will be the primary driver of cultured meat,
Mm,
because
mm,
meat factories currently have margins between 5 to 15%, depending on how well they're run and how good of a year it is. So we're
yep.
talking about significant increases in the profitability of meat facilities. And that's why we are taking this to the big meat players and being like, you guys can continue building factory farms and slaughtering all these animals, or you could build this other type of factory and make more money, but also not have to induce the suffering of billions of animals, and also not having to destroy the natural world in order to make the meat.
For someone who's not a scientist who doesn't understand the optogenetics that you do, can you, in like a very for dummy style, explain how this light, like, how does this practically work in the bioreactor? How is it working? Talk about it.
Yeah. So at a high level, all that Prolific does is bring things together and separate them using light. So we use these naturally occurring light-sensitive proteins that exist in all plants, all algae, all cyanobacteria, and we are eating them all the time. So every time you eat a salad, you eat a bunch of light-sensitive proteins. So what these proteins do is they have one shape in the dark, and when you hit them with light, they change shape with a particular wavelength of light. And when they change shape, they bind to each other with extremely high affinity. And so we just take advantage of the fact that these proteins bind to each other when you hit them with light, and we attach them to various different things inside the cell. You can attach them to receptors, you can attach them to enzymes, you can attach them to anything, any protein. And so this gives us a way to control every aspect of the cell just by shining different wavelengths of light on the cell. And there are many different ways to uh, illuminate these reactors. And so we have genetic tools that we put into the cells that give you control over different pathways with light, depending on what our customers want. We have hardware where we'll send engineers to the customer's facility where we'll retrofit their reactors with illuminators. And we also have software, which is basically an AI agent that will learn over time what the right light pattern is to use, because it's not the case where you just switch on the light and you leave it on. It's the case where you pulse the cells with light.
Mm.
Different pulsing patterns do different things. And you can train an algorithm to figure out what the right light pulsing is. And these pulsing patterns can get better and better over time. So your performance can get better over time, which means that you can bring on more customers, which means that you have more data, which means that you can make even better predictions on the light patterns, which means that you have even better performance. And so you just keep turning this crank.
To get nerdy on the implementation on the hardware, I just had a conversation with Paul Shapiro from Better Meat Co. He's thinking a lot about biomass fermentation with around mycoproteins, and he's talking about how there's proven science and lots of hardware out there that you could do around biomass fermentation. What does this look like? Is this something where you have to recreate the bioreactor?
Yeah, you do not need to recreate the bioreactor. You can use existing bioreactor infrastructure, and our illuminators can slot into that infrastructure. As many different forms of illuminators. You can have them as a external flow through system. You can have them on rods. You can have them on impellers. There's a whole bunch of different ways that you can do this. And there is no single best way to illuminate the cells. There is only lots of different types of hardware that you can use to illuminate, which gives you different amounts of precision over the cells, and different genetic tools that require different amounts of precision.
Got it. Okay. You said you're having conversations with big meat companies.
Not just big meat, but also, big pharma, CDMOs, the startups.
I would imagine that maybe there's different sorts of reception. I'm thinking like the venture funded guys have already spent $100 million on this. Are they like, oh great, we finally found a way, or like are they like, oh man, I sunk all this money in the old way?
Yeah, well, I'd actually say that they haven't sunk money into quote unquote the old way, because any capex investment that you have made, our technology can slot into it. And any cell line that you've developed, our technology can slot into it. So whatever you've done, it's not wasted work. Our technology can fit into it. So I definitely would disagree with the fact that they've wasted money. And so the reception has been incredibly positive. I mean, since we announced what we were doing about 4 weeks ago, and yeah, it's been overwhelmingly positive.
On the big established meat companies of the world, like the Tysons of the world, the Purdue's, are they strongly interested? I mean, I think a lot of them are, hey, it doesn't matter how, we ultimately just want to produce a product. We don't necessarily have to rely on animal agriculture, because some of them have definitely explored cultivated meat. What are those conversations like?
I'm not going to name any names because I've signed many
Sure.
confidentiality agreements, but what I can say is that there is very strong interest in the big food companies, both in big meat and in big dairy. I think what you'll see is that the early movers are unlikely to be the big meat companies. I think the early movers are going to be the cultured meat companies and or the companies that are getting into cultured meat from a sort of parallel industry like amino acid production or dairy protein production, and they will be getting into cultured meat because they see the opportunity and the demand for meat doubling and this resource constraints leading to not being able to double the supply, et cetera, et cetera. So if you're a big meat company, you're probably looking at this being like, well, I already make a ton of money from slaughtering animals. I don't really need to be a first mover in what is going to disrupt my core business. And so I think what you'll see is first movers arising from people who aren't making money on slaughtering animals. But then, for a combination of greed and fear, you will rapidly see all of the big meat companies building cultured meat facilities because they will be forced to. Because if our hypothesis is true, and growing meat with light leads to a margin profile that is so much higher than producing factory farms, they actually don't need to care about the animals and they don't need to care about the environment. They just need to care about making more money. And I trust them to care about making more money because all of them have fiduciary responsibilities to maximize their shareholder value. And so I believe that they will all switch over purely because they'll want to make more money, and this will be the way that they can do that.
When I look at like the existing chicken farming practices and how commoditized, how low cost they've been able to get that, it's hard for me to see how you could get lower cost on that. So walk me through how you get higher margins with what you're doing with all the steel and bending metal, how you can actually get there.
So let's think through the cost stack for meat production. The biggest bar in that cost stack is the media. So the media is the sort of soup that you grow the cells in.
Yep.
There's four components to that. There's water, there's sugar, there's amino acids, and then there's signaling molecules. The signaling molecules are by far the most expensive of those four, so they make up about 90% of the media costs. We don't need them. We can eliminate them with light. So our media will have only three components, which will be water, sugar, and amino acids. The water is very cheap. Sugar is very cheap. Amino acids are comparably more expensive, but still pretty cheap relative to the signaling molecules. But basically, the majority of the input cost is solved by using light instead of the signaling molecules. Okay, so we move on to the next part of the stack, which is CapEx. That becomes the next biggest thing. And there's two ways to address the CapEx issue. One is you can get more productivity for your CapEx investment. So if you have a way to increase the yield that you can get per bioreactor, it reduces the effective cost of the bioreactor. And light is a way to do that because you can experiment with the different patterns of light, and some of those patterns lead to very large yield advantages. And so light effectively reduces the cost of your CapEx because you can get more product per unit time, per unit volume using light than you can with molecules. So that's the sort of indirect way to address the CapEx issue. The direct way to deal with the CapEx issue is to reinvent the bioreactor, and some people are doing that. And so I suspect that you will see in the next few decades, people will invent new types of bioreactors that will probably be stackable. They'll probably be made out of plastic, not stainless steel. And so I think there'll be a bunch of innovations there that will reduce the cost of the CapEx. The next part of this cost stack is labor and people. And Prolific can help with that as well, because obviously the big picture vision here is to build machines that can control biology. And so our bioreactors will be the first sort of quote unquote smart bioreactors where they'll be able to understand what's going on, and they'll be able to directly interact with the cells by using light and experiment and find better and better light patterns over time. And so um, it will be largely autonomous how these reactors work. So you won't need to
Hmm.
hire lots of people in order to run these facilities. The reactors will run themselves for the most part.
The light as growth media in terms of productivity, say it took you 3 months to create certain X pounds using the traditional, stew of, proteins, etc. How much faster is it with light?
So it's very light pattern dependent. So we found some light patterns that will give you no yield advantage, some light patterns that will give you a modest yield advantage, and some light patterns that will give you a very large yield advantage. So we found, for example, some patterns that will give you 100% yield advantage over the optimal dose of the growth factor. And what's very exciting to me is that we don't really understand what the ceiling is on these things because there is so many different light patterns that you can experiment with. And we have tested a tiny proportion of the possible search space here. And so we found patterns that can lead to 100% yield advantages, but searching only 0.00001% of the possible search space. And so what the true ceiling is on performance, we don't know. But we do know that we can massively outperform molecules.
You did say milk, so I want to ask you about that part. So you have dairy company. You said dairy. So how is this used in a dairy context?
Yeah, so you can use this technology in cow cells. So you can grow up the cow cells using light, and then you can also use light to get the cow cells to produce dairy proteins.
Mm-hmm.
Um, So this is a concept that we patented and invented called the refinery model for cultured meat, where you can grow up the cells using light and then produce high-value nutritional proteins using light, like lactoferrin and osteopontin and bovine immunoglobulins, et cetera, et cetera. And these proteins are very valuable, and you can sell them as baby formula and supplements and all sorts. And then you can take the cow cells and sell them either as an ingredient to a flavor house, or you can build a meat brand and sell it to the consumer as meat, or you can mine them and you can mine interesting components of those cells, like phospholipids, for example, and then you can sell those as specialty nutrition products. So there's all sorts of interesting ways to monetize this.
What does the meat company of 2045 look like? Are they having cows on farms anywhere? Are they? Is it all just meat companies? Are just companies with big warehouses filled with big metal tanks or maybe plastic tanks? How do you see the 20 years in the future?
I think that 20 years in the future, what you'll see is cultured meat will have gone from something which most people think is impossible to something which is being scaled and deployed rapidly all around the world. And I think the hardest part is going to be the first full scale facility getting built, which I think you'll see in the next 5 to 10 years. And after that first facility gets built, it will be like a gold rush. Everyone will start building cultured meat facilities for a combination of greed and fear, because it will be both an offensive move and a defensive move for them. And they'll be forced to, because if they don't, their competitors do, you won't be able to compete in the market with a process that is so much lower cost and so much more profitable, because your competitors will just be able to bring down
Mm.
their prices and you won't. And consumers are very price sensitive, especially on meat. And so you will be forced to adopt this technology as a large meat company.
This does seem like a strategic food sovereignty type of thing. So if I'm like Taiwan or like
Mm-hmm.
Japan and I want to produce, I don't have enough dairy or farmland to produce this. I can see state capital starting to go into this. Are you hearing that? Is this like hearing this is a big strategic move for nation states?
Very much so. So again, I've signed many confidentiality agreements, and so I can't name specific names, but I can say with 100% certainty that states are looking into this, and the large sovereign wealth funds are going to be deploying hundreds of millions of dollars and then eventually billions of dollars into this. And the reason why they're going to do that is because, one, they can make a ton of money, but two, and more importantly, this is a food security issue for them, and it will have a number of additional benefits. Like reducing the amount of zoonotic diseases, reducing the land use, making them more, you don't have any methane, you have to use less land, less water. And this technology is also useful outside of food. So you can also use it to make medicines. You can use it to eventually grow plant cells, there's so many things that you can do with biology that if you have a better toolkit, the scope and scale of biology, if expanded, is a dramatic and extremely compelling economic opportunity for countries.
Well, Deniz Kent, CEO and co-founder of Prolific Machines, this has been fantastic. Thanks for spending time with me.
Thanks for having me.
That's it for the Spoon Podcast this week. Deniz Kent with Prolific Machines, creating a new way to grow meat cells using light. If you haven't already, please rate and review the podcast on Apple Podcasts or Spotify. It really does help, and we will read your review and give you a shout out in upcoming episodes. All right, folks, that's it for now. We'll talk to y'all soon.